Good afternoon, everybody. So today we are going to discuss remote sensing and GIS application in soil erosion modeling and watershed prioritization. So to begin with, let us try to understand how the soil is being formed. As we all know, soil is formed through a process we call weathering. So that weathering mainly due to the natural weathering process, where you can see in this slide that the parent material rock, if the crack is there, due to force of wind, rain, hail, ice, so because of heat and cold, there will be mechanical weathering, so that parent material will be disintegrated into small particles, and that's how the soil will be formed. So there will be a natural rate of soil formation. And now to discuss soil erosion. Soil erosion, you can say soil erosion is the detachment and subsequent removal of soil particle from terrain surface due to the action of physical forces such as rainfall, runoff or wind. So because of any physical force, if the soil is being detached and removed from its position from a terrain, then we can call it a soil erosion. Now it's not that soil erosion occurs because of human interventions only. As there is a natural process of soil formation, there is a natural process of soil erosion also, but the rate of soil erosion in case of natural soil erosion will be very less, so it's called as background erosion. And another one is accelerated erosion. As the name indicates, it is the accelerated rate of soil erosion, and the rates get accelerated because of human activities. That's why we call it as a accelerated soil erosion. Now, as we have seen, to occur soil erosion, there must be agent causing that erosion, and we mainly deal with two kinds of agent. One is your wind erosion, another is your erosion because of water. So water and wind are the agents of erosion. So as you can see, wind cause erosion in different types, water cause erosion into different types. Just to have a knowledge, we'll discuss wind cause erosion in which types. So majorly the wind erosion is classified into three classes. One is your roll or sliding, another is your saltation, and third one is your suspension. So roll or creep or sliding, as the name indicates, because of force of wind, the particles will roll over the surface or they slide over the surface, and that is called as roll. Or in other form, the particles will jump like the bungee jumping. They'll jump, so they'll join the air, and it will again, because of their weight, they'll again fall down on the surface, so they'll jump, and this is called as erosion through a saltation process. And the third one, as the name indicates, suspension. The lighter particles will get suspended into the air, and they'll travel miles away from their source. So whatever we see, the sandstorms, is the effect of erosion due to suspension. So if we just see what kind of particle will be subjected to what kind of erosion, for saltation to happen, the typical particle size would be 1 mm to 0.5 mm diameter, and 60 to 90% of wind erosion will occur through saltation. Whereas for creep, obviously the particle size will be bigger than the saltation, so particles having diameter more than 0.5 will be subjected to erosion in terms of creep or roll over the surface, and around 7 to 25% of wind erosion will occur in this type. Whereas for suspension to happen, the particle size should be less than 0.1 mm, and 3 to 10% of the wind erosion, only 3 to 10% of wind erosion occurs in terms of suspension. Now, as we know, particle to be moved because of by wind, the particles must be light in weight enough to be moved. They must be free to move. So as we know, if the soil is moist, wind will have very less effect on that soil, or if the soil is covered with vegetation, wind will have very less effect on the soil, or they will create very less soil erosion. So what is the general requirement? That there should be a wind of at least 10 miles per hour velocity at height 1 feet above the surface. So if this or above wind is there, loose particles of soil will get eroded due to wind. Now if we have to model the soil erosion due to wind, what factors we need to consider? The factors are soil erodibility index. So it's a tendency of soil to get eroded, soil roughness, the climatic factor, the wind velocity and soil moisture, the field length factor, and the vegetation cover factor. So all these factors affect the wind erosion. But today's lecture is not about the wind erosion. We are mainly interested in erosion due to water. So as we know, there is a geological erosion rate and there is an accelerated erosion rate. So the accelerated erosion or erosion because of water as an agent is called as water erosion, and as the wind erosion is classified into different classes, same water erosion is also classified into different classes based on what is the driving force behind that erosion. So you can see here, or I'll show you a figure. So this is a typical different types of erosion. So this is a typical, you can say, watershed scenario where on the ridge you have a vegetation and the erosion will occur just because the kinetic energy of droplet is transmitted to loose soil and the soil is being detached from its original location and is transported from its original location. So this kind of erosion is called as splash erosion. As you can see, the erosion occurs because of splash action of the rainfall. And now when there is a rainfall, the water will be absorbed in the soil and the excess water will start as a surface runoff, and that surface runoff will flow as a sheet over your soil surface, and that flowing sheet will carry the loose particles of soil, and that kind of erosion is called as sheet erosion. Now because of heavy surface runoff and undulation on the surface, this surface water will make a reel or a channel, and erosion in this channel or reel is called as reel erosion, channel erosion or gully erosion. Now many of these reels will join together and they form a channel or a stream, and that stream, because of high velocity water, will erode its bottom and its sides. That is called as stream bank or channel bank erosion. So these are the different types of water erosion. Now if you can see, a raindrop having with a typical velocity of 20 to 30 feet per second will have a sufficient amount of energy to displace a soil particle 2 feet above its original location vertically. So if you talk about any other angle, obviously it will be more distance. And you can see here a typical particle of 1 mm will travel with a 15 km per hour velocity. If the drop size of that particle is increased to 5 mm, the velocity will be 32 km per hour, and the erosive energy of that energy will be 500 times the original, because the equation is mv square. So not only the mass but the velocity will increase with the increase in diameter, so its erosive power will increase. So we know if the droplet size is bigger, the erosive power of that rainfall will be much higher. Now we have seen this, if the erosion is because of splash action, it is called as splash erosion. If it is because of the uniform sheet of water flowing over the surface, it is sheet erosion. If it is because of concentrated water in a reel, it is reel erosion. If multiple reels join together, it is a gully erosion. And then it will, the erosion between reel and surface is called as inter-reel erosion. And the total sediment or soil moved out of any watershed is called sediment yield of that watershed. Now you can see here, this is a very lush green landscape where the vegetation acts as a conservation measure. Vegetation do not allow the raindrop to directly impact soil, neither it allow the surface runoff to carry this particle. So there is no soil erosion here. But if the vegetation cover is being removed or if it is being degraded, what will happen? The raindrop will directly impact the soil and it will cause a splash erosion. The surface runoff will try to move those removed particles as a sheet erosion. That surface runoff will join the reels and it will create a reel erosion. Those reels will join, multiple reels will join together and they will form a stream, causing a stream erosion, and a heavy discharge stream will cause this kind of stream bank erosion. As you can see from here, you cannot convert a landscape to original position, but you can convert the landscape to its original when maybe from this position when there is a reel erosion in your area. So you can check the reels, you can improve vegetation in your area so that there is no splash erosion, there is no sheet erosion. So when the runoff and the soil joining these reels is minimized, so effect of these reels will be minimized. But after this, there is no coming back to the original scenario. So we have to apply the conservation measures before that. Now let us try and see what is the status of soil erosion. Is it really a big problem, or is it just another scientific topic? So just to discuss, I'll try to highlight some things that globally 175 million hectares of land is degraded because of soil erosion. The current rate of annual average soil loss ranges from 20 to 100 tons per hectare. And the rate of erosion is 16 to 100 times more than the natural soil accumulation rate, which is 1 centimeter of soil will be formed in normal agriculture practice in 200 years. So you can see it would take 200 years to form 1 centimeter of soil in a standard agriculture practice, whereas the erosion rate, the present erosion rate globally is 16 to 100 times faster than the soil formation rate. Now you can see the material delivered from rivers to ocean has increased from 8 billion tons to 23 billion tons, and Asian rivers contribute 10 billion tons out of this 23 billion tons. And if the present rate of soil erosion continues, we will lose our top soil resource, or the cultivable soil, 30% of cultivable soil by 2050. So yes, this is an alarming problem and we have to deal with this. Now we have seen what is a global scenario. Just to see what is the Indian scenario, you can see about 5,334 million tons of soil is being detached annually due to agriculture and associated activities in India. The country's river carries something around 2,052 million tons of soil every year to the ocean. Nearly they carry this much of soil. Nearly 1,572 million tons is carried to the ocean, and the remaining, where the remaining goes, remaining is deposited into the reservoirs. We'll see in coming slide what is happening to the reservoirs. Around 480 million tons soil is being deposited in various reservoirs, due to which we are losing 1 to 2% of storage capacity of each and every reservoir. I'm just trying to highlight here. There are these are few reservoirs where you can see the Ichari Dam, which is on Tans River, which is a tributary of Ganga. The loss of capacity is almost 5% every year. So you can see after 20 years, this reservoir will be of no use. The entire life storage will be filled with the silt, and it is not possible to desilt these kinds of reservoirs. It's a very costly affair. So what we can do, instead of doing that, we can trap this soil before it reaches the reservoir, and to do that we need to know the process, we need to model the process. So we need to know how much soil is coming, from where it is coming, and if we have to trap it, what we should do. So that's why it is important to model the soil erosion. And because the soil erosion is dynamic, it varies in space, it varies in time, so we cannot do it using traditional techniques. Now it is not preferred to do it using traditional techniques, so we can use the remote sensing and GIS technique in this aspect. Now I'll try to tell you, I'll try to demonstrate through case studies how you can do that. So I'll try to demonstrate through 2 case studies, where in first case study we will use revised universal soil loss equation developed by USDA to model soil erosion for entire country. I'll say to model potential soil erosion for entire country. In another case, we'll try to use Morgan-Fenney model to model soil erosion for a basin, for a watershed, and then we'll try to see how to prioritize the watershed using these results. So first case study, the objective was to actually study or estimate the potential soil loss from entire country using revised universal soil loss equation. So I'll first discuss why this alternately called as RUSLE or RUSLE or revised universal soil loss equation. So this method is used worldwide. It is mostly accepted. It is accepted because it is not data extensive. It requires very less amount of data which is easily available, and because it is very simple in nature, you can club this model with GIS platform. So that's why it is very widely accepted. Now this is how the revised universal soil loss equation looks like. It is alternately known as RKLSCP model, where RKLSCP, all these parameter represents some process or input in soil erosion modeling, where A is your annual soil loss in tons per year per hectare. Now this revised universal soil loss equation originally was given in 65. and it was revised in 1975 by Renard. So then it is called as revised universal soil loss equation. There is one more variant of this equation called as modified universal soil loss equation, mostly. So it's USLE, revised USLE and modified USLE. So we're going to use the revised universal soil loss equation, where A stands for average annual soil loss in tons per hectare per year. R stands for rainfall runoff erosivity factor. K stands for soil erosivity factor. So R stands for erosive power of the rainfall and runoff. K stands for soil erodibility, its tendency of soil to get eroded. L stands for slope length factor. S stands for slope steepness factor. C stands for cover management factor, and the P represents the conservation practice factor. So all these factors do have a multiplicative effect on each other. If the rainfall is more, it will increase your runoff or soil erosion by that much of multiplier. It will not add, it will multiply. So that's why the relation between all these factors is a multiplicative one. So now we have to derive all these factors. We have to derive R, K, L, S, C, P. So obviously, because it is a rainfall runoff factor, so I need some rainfall information. Because this is a soil erodibility factor, so I need a soil information. Because these two are the terrain factors, so I need terrain information. This is a land cover, cover management factor, so I need maybe the land use, land cover, or the cover information. And because this is a conservation practice factor, I need information about kind of conservation practices performed in the watershed or in the study area. Now, because the study area here is the entire country, you can see the beauty of this model. You can apply this model on a simple pixel, or you can apply this model to the number of pixels representing a watershed, a basin, a state, or a country. Because this is a pixel. Now we are trying to apply it on a pixel basis, so doesn't matter to what area you are applying. So here we are trying to apply it for entire geographical area of the India. So we are going to use the DEM. So here, because the area was large, so we have used the Hydro 1. So it's actually GTopo 30 arc second DEM, where if I project it, the pixel size will be something around 1 kilometer. So 1 kilometer DEM I am using. Now land use land cover map. You can develop your own land use land cover map, but because the study is country level, so we had available land use land cover map developed using spot NDVI data. This land use land cover map was generated in IIRS Dehradun. So we have used it. So there are 40 land use classes, and those land use classes do have the organic matter content as the attribute information. Use the, as you can say, the composite of annual NDVI map for the same year. You can use a representative NDVI, but why we have used composite? Because the erosion will occur because of rainfall, and the rainfall typically in India is concentrated in rainy season, but we do get rainfall in winter season and summer season also. So if I take a vegetation condition of particular season, it will not be the true condition for other season. Like in summer season, there will be very less vegetative cover, whereas in rainy season, the vegetative cover will be very thick. So if I take a vegetative cover for a rainy season, it will not represent the actual vegetation condition in summer season. So instead of taking a vegetative condition of a single season, we have selected a composite annual NDVI map. Then soil map, you can use any soil map available to you. Here we have used the soil map available with the FAO, where we had all the land use, the soil types in India. So the attribute information was soil type. Actually, I should say the soil texture, the percentage of texture, its soil structural code, soil permeability code, and the organic matter content of each soil. Now, luckily, we have this information in the attribute table. If you don't have this information, even with the soil texture name, you can find out using any standard table how much will be the sand, silt, clay, structural code and permeability code of that soil. And this information, if not available, the organic matter content in your particular soil, if it is not available, what you need to do is you need to club your soil map and your vegetation map, and there are standard tables available which will tell you if this is a standard land use in this soil, what will be the organic matter content, and from that fusion you have to derive this organic matter content map. Then rainfall map. Nowadays, IMD also provides the gridded rainfall for entire country, whereas we have used the Climate Prediction Center NOAA's CPC data, which was of 10 kilometer by 10 kilometer resolution. We have used that. Now you can use even the IND data, which is of 25 kilometer by 25 kilometer resolution. Now this is how the flow chart of this entire process looks like. So we will use the DEM. From DEM we will derive the topographical parameters, which is L factor and S factor, the slope length factor and the slope steepness factor. We will use the rainfall data and we will derive the R factor, which is the rainfall erosivity factor. We will use the soil map, and from soil map we will derive the soil erodibility factor. If the organic matter content is not available in the soil map, we will fuse that soil map with the land use map. We will find out the organic matter content and then we will derive the soil erodibility factor. From land use map we will derive the conservation factor, and from land use map or vegetation index map we will derive the cover management factor. And all this will be done in the environment of GIS or any image processing software. So now we'll see, this is a typical equation for R factor, which is a rainfall erosivity factor. Originally it is also called as EI30 factor, where E represents the kinetic energy of erosive rainfall and I30 represents the maximum intensity of rainfall during period of 30 minutes. So this is the kinetic energy. Kinetic energy can be calculated if you know the average intensity of your rainfall and total amount of precipitation in that storm. But to calculate the R factor for entire year, what I need to have the recording type rain gauge data, because I need intensity. Intensity can only be calculated using recording type rain gauge data. Now we don't have these large number of recording type rain gauges in India. Now to overcome this problem, Ram Babu et al. Has proposed, or they have derived some relation between annual or seasonal total precipitation and the this YA or YS in the R factor in season or R factor in a year. So this relation we have used, where we require only pixel based annual rainfall. So we will use this equation and we have calculated the rainfall erosivity factor for entire country for a year. So now one factor we have calculated. Now C factor. C factor is nothing but it's a cover management factor, which says that if you have very dense vegetative cover, so the rainfall will not directly impact your soil. Since the rainfall is not directly impacting your soil, there will be a zero erosion. So your erosion will be zero. So if you can see your original equation, I'll try to show you that equation here, that your annual soil loss needs to be zero. Now you have some rainfall, so R factor cannot be zero. You have some soil, so K factor cannot be zero, because the topography is having slope and slope length. The L and S factors cannot be zero. You may or may not have some conservation factors, so P factor cannot be zero. But because thick vegetation, no soil is being eroded from your area, but so your annual soil loss needs to be zero. So in this entire equation, only C can be zero. This cover management factor can be zero. So what this cover management factor is, that if your vegetation is very dense, so dense that your rainfall is not penetrating to the soil, and because of that your erosion is zero, your C factor should be zero. In other words, if your NDVI is 1, which represents a very thick vegetation where your raindrop cannot penetrate to the soil, NDVI 1 means very thick vegetation. So at that case your C factor should be 0. And if your NDVI is 0, on the contrary, if your NDVI is 0 means there is no vegetation on the soil, so your erosion rate will be the highest. So the C factor can be 1. That's how. So you can see there is an inverse relation between C factor and NDVI. If NDVI is high, C factor will be low, and if NDVI is low, C factor will be high. And the limits are, NDVI can range from, if we exclude the water and ice, NDVI can range from 0 to 1, and C factor also ranges from 0 to 1, only inverse. So we have exploited this inverse relation to derive the C factor based on NDVI. And mind you that this is not a simple NDVI, this is a composite NDVI. This is a composite of entire year. So if your vegetation remains thick and very good throughout year, your NDVI will be high in that duration. If your vegetation in one season falls down, so your NDVI will have very less, or you will have less value. So accordingly your C factor will have, wherever your NDVI is having high value, your C factor will have less value, making your soil erosion less. Wherever your NDVI is poor, your C factor will have high value, making your erosion higher. So this is how we have derived the crop management factor. Now soil erodibility factor. There is a standard equation to calculate soil erodibility factor where I require this organic matter content in the soil. I require this primary product of size fraction like sand, silt, clay. I require this structural code, I require this permeability code, and I can calculate the soil erodibility factor. Luckily, all this information was available in the attribute table of my soil map, so I have directly calculated the soil erodibility factor. Now to calculate conservation practice factor, what this factor says? This factor says that if there is some land use, let us say for agriculture. Now agriculture land will invariably controlled by agriculture bunds. Every farmer will have its own agriculture boundary delineated by the agriculture bunds. Those bunds act as a agriculture delineation boundaries also, plus water and soil conservation structure also. So no matter how much rain is occurring in that area, soil is detached, but that entire runoff is not being carried out of that area. So the soil is not being transported out of that area, so it will not by the definition of soil erosion. So in that case, though because of rainfall, because of soil type, because of land use, because of topography, the soil is being detached, but because of conservation practice, the soil is not being removed out of that land, so total soil loss will be 0. And we can represent that condition by giving value P factor value 0. So this conservation practice factor will range from 0 to 1, where represents no conservation practice, and 0 represents very highly effective conservation practice, because due to the soil is not being eroded from that area. So this conservation practice will depend upon the land use, and we already have the land use map. So we have referred to the standard tables available in C.T. Hahn's book, and we have given these conservation practice values in your land use, and we have converted our land use as a conservation factor. Now only remaining factor are the topographical factors, the slope length factor and the slope steepness factor. Now as you can see, the slope length factor, the effect of topography on erosion in Rusley is accounted for by LS, and where L is the slope length factor. So the slope length, we need to know what is the definition of slope length. We are saying slope length factor, but what is a slope length? So by definition, slope length is a horizontal distance. The word horizontal distance is very important. Horizontal distance from the origin of overland flow to the point there are points. So the starting point is the point from your overland flow starts to the point where the gradient of slope decreases enough that the deposition begins, or the runoff becomes concentrated into a defined channels. So any one of this point and the point from where your surface runoff begins, the horizontal distance between these 2 points is called as slope length. Now this is the equation to calculate slope length factor, where this lambda represents the slope length. This is a slope length factor, and this 22.13 is a typical plot size using which the Rusley model. Actually the Rusley model is an empirical model. Empirical model means the Rusley model is being developed using field observed data. Thousands of field plots were laid down and the data was collected, and the field plots were of size 22.1. The length of those plots were 22.13. So the slope length factor tells us that what is the slope length of your field with respect to the slope length of the original plot size, and what effect it will have on your erosion. So I need to know the slope length. Now in GIS, and this exponent m, can also be calculated if you know the slope of your area. So generally nowadays we don't calculate this, because this exponent m universally it is being accepted that 0.14 will be the exponent for the watershed. So now this is a slope map of entire country. So for entire country, average m comes out to be 0.19. If I refine it, because these areas are very steep slope area, that's why the value is coming high, otherwise it comes something around 0.15 or 0.14. Now you can see slope length. What is the slope length? Slope length is nothing but the flow accumulation into grid size in GIS format. But the condition is the grid should be an overland flow grid. If your grid falls is falling under overland flow grid, you can use this equation to calculate the slope length, and you can replace the m here by 0.14, or m you have calculated on the pixel by pixel basis. So now you have calculated the slope length. Now the only remaining factor is slope steepness. So in revised universal soil loss equation, the slope steepness is calculated as a two-part. If your slope is less than 9 degree, you can use this first equation. If your slope is greater than 9 degree, you can use the second equation. In original USLE, because the original universal soil loss equation was developed for agriculture watersheds only one slope range was available. Whereas in revised universal soil loss equation, there are two slope ranges available. So we have calculated the slope length for entire LS factor for entire country, and the average soil loss for the entire country we have calculated, and you can see the average soil loss of this of entire India comes around to be 18.69 tons per year per hectare. Now it is very difficult to actually calibrate or check these results against any observed data. So what we have done, instead of seeing this data for the entire country, we will try to see what is a basin wise scenario. So all the major basins in central and northern India, we have extracted from this soil loss, and the average soil erosion rate of each of the basin is being tabulated here, where you can see the Luni basin. We all know the Luni falls under Rajasthan and Gujarat, where very low rainfall is there. So the soil loss is also very low. It's 8.66 tons per year per hectare. Whereas in Satluj basin, the average soil loss is 35.18 tons per year per hectare. And then we are trying to see why this difference. And as you can see, we try to find out what is the C factor, K factor, P factor, annual rainfall, R factor, slope factors, or the average slope. And you can see in Satluj, almost the annual rainfall is very high, so the R factor is high. The slope, average slope of entire basin is very high, that's why the S factor is very high. And C factor compared to Luni Ghaggar basin, the C factor here is cover management factor is less compared to the Luni Ghaggar basin. That's why the total erosion from Satluj basin is very high compared to Luni Ghaggar basin. Now we try to see our results, and we try to compare it with the information available in the literature. The average potential soil erosion in entire country from our calculation was 18.69 or 18.66 whatever tons per year per hectare, and the earlier reports given by CSW CRTI Dehradun suggest that the average annual soil loss from country is 16.5 tons per year per hectare. So we can say that it is pretty much close to each other, because for a country scale this much difference doesn't actually count. Now for a river basin, as you can see, out of 10 river basin, potential soil loss in 8 river basin except the Mahanadi and Satluj is within the range of 8.66 to 15.69. So it is well within this limit. Now average soil loss from Ganga basin from our calculation comes out to be 11.56 tons per year per hectare, and there were available from previous studies done elsewhere. Those results says the average soil loss from Ganga basin is in a range of 5 to 10 tons per year per hectare and 10 to 20 tons per year per hectare. So you can say the results what we have got is almost close to both the results. It is here the highest range is 10, we are getting 11. Here the lowest range is 10, we are getting 11. So we can say it is within the range published earlier. Now the highest soil erosion rate is in Satluj basin, and we have analyzed it is because the terrain is very rugged, slope is very high, rainfall is very high, and not the vegetation condition not always remaining, it doesn't remain constant throughout the year. And this entire exercise demonstrates the applicability or capability of Rousselet to work at even at a larger area of scale, and it is acceptable to watershed scale also. In second case study, we'll try to see how we can use remote sensing GIS to model soil erosion using another very famous model called as Morgan-Morgan-Feney, alternately known as MMF model. So again, why MMF? Because it is a semi-based, I will not say it is a process-based, it is a semi-process-based model. It do have empirical parameters in this model also. Then it was designed to predict soil loss from hill slope watersheds. Most of the soil erosion models are developed for agricultural watersheds, so they do not give accurate soil loss when you apply those models to a hilly watersheds. But this kind of model, this MMF, is particularly designed for hill slopes. Now, when this model was actually validated, so it gave a very good result in 47 out of 67 sites in 12 countries worldwide. So the what you can say, success rate was 70%. And when the people considered that the sites, 30 sites, where the observed data about soil properties, out of the 67 sites, only 31 sites the observed data about soil property was available. When only these 31 sites were considered, the success rate was improved to 90%. And say, when the data, accurate data was, field data is available, the success rate is something around 90%. And this model is very easy to integrate with GIS and remote sensing platform. That's why we are trying to we will try to do this. So in MMF model, actually the process is being divided into two phases. One is your water phase and another is your sediment phase. In water phase, first of all, we'll try to calculate the kinetic energy of your rainfall. Then we'll try to calculate the discharge in your rainfall. Then in sediment phase, we'll try to calculate the detachment due to drop, and we'll try to calculate the transport capacity of your runoff. So this is a first MMF model. Now there are three variants of MMF model: MMF, then your revised MMF, and modified MMF. So we'll try to see the MMF and revised MMF. So we'll see one by one. First of all, to calculate the kinetic energy of rainfall, what you need the total rainfall and the intensity. Now you can see this equation is almost similar to the equation that we have used or we have seen in revised universal soil loss equation, where in EI30 factor the kinetic energy was calculated using same kind of equation. Now this equation is a kind of empirical equation which will vary from region to region. Now this particular, what you are seeing here, was developed for European condition and holds good for the United Kingdom and surrounding area, but this equation will not be valid, or it will not be proper to use in Indian context. So we have to see, or we have to see for the alternative in well, there are research available and people have published equations available for different climatical zones. So what I need, or what we need here is, we need the total rainfall in a year and we need the average intensity of all rainfall events. So this is the information what we require to calculate kinetic energy of rainfall in water phase. Another thing that we require in water phase, or we calculate in water phase, is the total discharge. To calculate total discharge, I require total rainfall. I require R0 is the rainfall per rainy day, so which you can calculate if you know the total rainfall and total number of rainy days. Total rainfall divided by total number of rainy days will give me the rainfall per rainy day. And this RC is nothing but it is a soil moisture storage capacity. This particular RC is the soil moisture storage capacity, which you can calculate if you know the moisture content of the soil, the bulk density, root zone depth, and the ratio of actual evapotranspiration divided by potential evapotranspiration. So this particular thing and root zone depth will be a property of your land use map. Bulk density and soil moisture condition, soil moisture content at field capacity. These two will be the property of your soil map. So if you have soil map, if you have land use map, you can calculate RC using some standard tables. So now what you need in water phase, you require the annual rainfall, you require the average intensity of all rainy events, you require the number of rainy days, so you can calculate rainfall per rainy day. You require the soil information like the soil moisture at field capacity, the bulk density of soil. You require land use map to know the root zone depth and ratio of actual evapotranspiration and potential evapotranspiration. If this information is available, you can calculate or you can solve both the parameters in water phase. In sediment phase, you can calculate detachment due to raindrop if you know the K factor of your soil. So K factor is the soil detachability index, which is nothing but the combination of your K, which is also similar to your K factor in Rousselet. Now this E is the kinetic energy of your rainfall and multiplied by exponent of 0.05 into A, where this A represents percentage of rainfall contributing to permanent interception and stain flow. So not all rainfall that falls on your surface will impact your soil. Some of that rainfall will be intercepted by your canopy, and that rainfall will either again join your soil as a stain flow or will remain on that canopy surface and evaporate. So that rainfall, effect of that rainfall, we have to remove from your kinetic energy. That's why we are multiplying this kinetic energy with exponent of minus 0.05 into water removed from your total rainfall. Now once this detachment is calculated, we want to know how much of the soil will be carried out of my area, and the agent that carries the detached soil is your surface runoff. So we want to know what is the transport capacity of that surface runoff, which can be calculated if we know the total surface runoff, the topography, the slope of my land, and the cover factor or the crop cover factor, which is a combination of C factor and P factor in your revised universal soil loss equation. So this is how a flow chart will look like. If I have rainfall intensity and rainfall value, volume, number of rainy days, I can calculate R0, I can calculate effective, I can calculate kinetic energy of rainfall. If I have soil map and land use map, I can calculate this soil moisture storage capacity RC, because and when I know the total rainfall, when I know the R0, when I know the RC, I can calculate the surface runoff or Q. Once I have calculated E and Q, kinetic energy and overland flow, my water phase is complete. Then I can move towards sediment phase, where I can calculate detachment due to this kinetic energy, and I can calculate the transport capacity of this runoff. And for a pixel, if I know this much tons of soil will be detached due to rainfall and this much is the transport capacity in that pixel, what I need to do is I need to compare this F and G. So you need to understand F is the detached soil in the pixel and G is the transport capacity of overland flow in that pixel. Let us assume if 5 tons of soil is being detached in a pixel, but the transport capacity of that flow is only 4 tons. So total soil loss from this pixel will be 4 tons only. So in that case, your soil erosion is transport limited. Whereas in another case, if only 2 tons of soil is being detached from this pixel and your runoff has a capacity to carry 10 tons of soil, but because only 2 tons is available, only 2 tons be carried out of your pixel. In this case, your erosion is detachment, or you can say the source limited. The soil is not available, that's why your erosion is limited by the source, erosion limited. Fine. So this is how the problem will be solved. Now this is a flow chart, more elaborate flow chart. In modified MMF, these are the terminologies we already have seen. Now in modified MMF, slight changes were done. In first case, what we were doing, we are trying to calculate kinetic energy by considering the total rainfall. Whereas in modified case, what we'll try to calculate the kinetic energy of effective rainfall, which directly falls on our soil differently. So the kinetic energy of that rainfall will be calculated differently, and the water which is intercepted by the canopy will again fall on the soil as a through fall. So that will calculate differently, but the and that is called as leaf drainage in this case. And the direct rainfall which is coming to the soil is called as direct through fall. So the equation for direct through fall remains same as we have seen in earlier case, whereas the equation for leaf drainage is a function of plant height only, and the total kinetic energy is summation of kinetic energy of direct through fall and kinetic energy of leaf drainage, and detachment due to kinetic energy detachment due to raindrop will be the same equation. Only thing, now here this exponent of e raised to 0.05, this thing will not be there because we already have taken care of this. The water intercepted, change in kinetic energy because of water intercepted, we have taken care here. So the detachment will be simply K, the soil erosivity factor, and the kinetic energy. So this is the detachment due to raindrop. One more change is being done in modified MMF, that not the entire root zone play a role in infiltration. Only the topsoil plays a role in infiltration. So why to consider the entire root zone? Instead, that root zone depth is being replaced by another parameter called effective hydrological depth. And that effective hydrological depth is being replaced here instead of RD, and the table shows if you have this these land use classes, what standard effective hydrological depth you should take. So annual runoff will be calculated by calculating RC, wherein the root zone depth is being replaced by effective hydrological depth. Now after doing that, in modified MMF, it is assumed that not only the raindrop will cause detachment, but also the flowing runoff will cause detachment. So in this case, not only the detachment due to raindrop, but also detachment due to runoff is calculated. And this is a very simple equation where this is a soil cohesive factor, Q is a surface runoff, S is the slope of your terrain, and this is your ground cover. It is nothing but a percentage of land covered by vegetation, which you can calculate using vegetation indices or land use map. And the transport capacity is calculated considering the C factor, Q factor, and the topography. Now the total detachment will be detachment due to raindrop plus detachment due to runoff, and this will be compared against the transport capacity. So if the transport capacity is less than the detachment, your erosion is transport limited, and if your detachment is less than the transport capacity, your process or erosion is source limited. So this is how we do. We'll try to compare it. We will try to see the case study where MMF was applied through watershed in Himachal Pradesh. It's a what you can Satluj basin. It's a sub watershed of Satluj basin. It's a Bata river basin. We have used temporal list 3 data and one PAN data also from IRS 1D satellite. Then we have used topo sheet, we have used meteorological data from observatory, we have used soil map. ILWIS was the GIS used here. So you can see this is a flow chart where from topo sheet the DEM was generated and the topographical factor slope was generated. From satellite data, the vegetation index, the land use map, and all associated parameters like the C factor, A factor, ET by E0 ratio, RD was developed. Now from soil map and meteorological data, this R0, R, then intensity from soil map K, soil moisture at field capacity, bulk density was calculated pixel by pixel basis. As you can see from land use, from remote sensing data, the land use map was developed for both the season Kharif and Rabi. From digital elevation model, the slope map has been calculated. From rainfall data, our annual rainfall is being, because there is only one rain gauge station, so we have assumed that for entire watershed same rainfall is applicable. Now this is a soil texture map. For this soil texture, the bulk density, the soil detachment index, the K factor, and the soil moisture storage capacity at field field capacity is taken from the literature, and these are the two values. I can see this is a soil moisture, this is MS. Sorry, this is a bulk density, this is a bulk density, and this is a K factor. Now we'll try to calculate this A interception average. We'll try to calculate using the NDVA map or any soil map. So A factor map, crop management factor map, map of ratio of ET by ET0, and topsoil rooting depth. All these maps we have developed for pixel by pixel basis, and this is actually, these are the results we'll see afterwards. From that, because R map is available with us, I map is available with us, we have calculated kinetic energy of rainfall. This is the value of kinetic energy of rainfall, because one rainfall was there, so same value remains for everything. But now because the soil and land use map, I mean there are two soil types and there are different land use, the RC, the soil moisture storage capacity, will vary. You can see there are number of soil moisture storage capacities because there are two distinct soil types and there are number of land use. So these two factors represent the soil effect of soil, these two factors represent effect of land use, so there will be different. So these are the RC values. This is a surface runoff where you use the RC, then you use the R0 and total rainfall. So we have the annual surface runoff map. We have calculated the transport capacity of that runoff. We have calculated the F detachment due to raindrop, and then we'll compare this F with the, sorry, I'll take you maybe few slides back where you can see two maps. Yeah, sorry. So this is a map where final soil loss is a result of comparison and assigning minimum value out of F and G, where you can see F is a detachment, G is a transport capacity. So whichever is less will be the soil erosion from that pixel. If my transport capacity is less, only that much soil will be lost from the area. If my detachment is less, no matter how much is transport capacity, that much only the detachment amount will be lost. So whichever is minimum out of this will be the soil loss from those pixels. So this is a soil loss map, and now that soil loss map we have sliced here. You can see we have categorized that soil loss map from 0 to 1 tons per hectare to more than 45 tons per hectare. So there are different classes. You can see these are the classes where high soil erosion or soil loss is being observed. Now annual depth of eroded soil, you can calculate this if you know the density of your area, so you know how much soil is lost. And then we try to analyze that under which land use the soil erosion is very high. So you can say this is a soil loss and maximum annual rate is this much, and the we will see in analysis what results are there. So you can say a distribution of soil loss among the slope classes. So how we have derived the, or we have calculated the average slope of all sub-watersheds, and we try to analyze under what condition the soil erosion is highest, or under what condition it is detachment limited, under what condition it is transport limited. So you can say for the watersheds having, sub-watersheds having slope 1 to 5 degree, it is the detachment and transport are the limiting factors for soil erosion. For this detachment and for this transport were the limiting factors. Similarly, we try to analyze under which land cover type or under which soil type the soil erosion is high, under which it is less, under which what you can say sub-watershed soil erosion is high, under which soil erosion is less, and these are the sub-watersheds having typically high soil erosion rates. So we try to compare it with what kind of classes we are trying to form. If this is the annual rate, if this is the annual allowable rate, almost 30% of this river basin or this watershed falls under severe soil loss condition. And then we try to see under what category, under what soil type the erosion is high, so that we can suggest some measures. So we can say there are three categories. For agricultural land where detachment is the main limiting factor, where the soil loss is limited because of detachment and it is high, what we can do, we can try to implement measures due to which the detachment of soil will be less. So all those will be the agronomic measures. Where agricultural land where the transport is a limiting factor, so what you can do, you can apply the mechanical measures like, or you can say civil measures like strip cropping, strip contouring, or grass strips, agronomy and mechanical measures. And for barren land, we need to restore that land. We have to grow vegetation so that the exposure of soil is minimized, so that erosion from this can be removed. Now, why we have done this? Because you cannot apply, maybe you have funds or resources available to conserve your soil, but they may not be available for entire watershed. So you may have limitation in resources, you may have limitation in fund or time, or you may have some particular objective, so you cannot apply those conservation measures for entire watershed. So you have to decide that which are the sub watersheds or villages or the spots. If I apply the conservation measures, I will get maximum output. And this process is called as watershed prioritization. So watershed prioritization is nothing but assigning priority or preference or weightage to one or more sub-watersheds from number of sub-watersheds within a watershed. Now, why we need to do prioritization? As we discussed, the resource constraint, that maybe the capital is constrained, the manpower is constrained, the time is constrained, or we may have some experimental or trial going on where we have to showcase our results very fast. So what are the different methods of watershed prioritization? First, you can do it based on soil erosion intensity. Now, you can do it by recognition survey, you can do it by soil and land use survey, you can do it by quantifying soil erosion where the models come into picture, you can do it based on socio-economic and demographic status of a watershed. So in first case, identifying the soil erosion prone area using remote sensing and GIS, features to recognize are you can see the tone, texture, physiography and temporal variation of your watershed. You can see if your watershed is vegetated, its tone and texture will be different. If your watershed vegetation is degraded, its tone, texture will go on decreasing with time, or the vegetation reflectance will be less and the bare soil reflectance will increase. So based on that, you can quantify the soil erosion rate and then you can assign the priority. Or you can use change in soil type or soil color or the dendritic drainage pattern. If the drainage goes on increasing with time, means erosion is happening. If the stones or the bare soil exposure is more, if the vegetation cover is degrading, so you can always assign erosion intensity class to those areas and you can do the prioritization. The factors which affect these erosion rates is the drainage, precipitation, vegetation health, elevation and the relief, and almost each of these factors you can monitor using remote sensing. So that's why there is a importance of remote sensing. You can calculate, you can derive land use map, you can do soil mapping, drainage network you can map or derive using DEM, geology you can map, landforms you can map using remote sensing data. Other techniques could be in quantifying the soil erosion, soil and land use survey method, where self-yield predictive model. So you can predict sediment yield based on the factors on which in your watershed the sediment yield depends upon. So in this case, the author has assumed that the sediment yield will be dependent upon ratio of average annual rainfall divided by average annual temperature, and the another factor is average slope, and another factor, third factor will be percentage soil particle coarser than 1 mm in top 2-inch soil profile. Then fourth factor will be the percentage of 2 micron of finer soil particles in top 2-inch soil profile. If you have this information, you can calculate the sediment yield or you can model the sediment yield from your watershed, and the areas from where your sediment yield is high, you can give priority to those areas. Other way of doing it, sediment yield index. Now this is a universally accepted method, sediment yield index, where the sediment yield, wherever your sediment yield index is high, priority will be given to that area. So sediment yield index is nothing but multiplication of area under particular erosion intensity, then the weightage assigned to that erosion intensity, then the delivery ratio of that watershed divided by area of that micro watershed multiplied by 100. Now wherever you have higher sediment yield index, priority should be given to that watershed. Alternately, there is another technique called watershed erosion response model, where you can take into account the morphological factors like drainage density, form factor, slope, the vegetation condition like vegetation density, or the soil properties like soil brightness index, and then you can assign weightage. So we'll try to see how using 3 case studies how watershed prioritization can be done, and based on your criteria how the prioritization results vary. So first of all, try to see this watershed erosion response model, where we'll use satellite data, we'll use field survey, and we'll use topographical data like the topo sheet or the DEM. So from satellite data we will calculate the vegetation index, and from satellite data we'll try to calculate the soil brightness index. From DEM or topographical data, we'll try to calculate morphological parameters like drainage density, form factor, slope of that watershed. We will assign weightage to each of these factors based on their importance in the process of soil erosion and yield, and the final weightage layer will be prepared, and the pixels or the sub watersheds having higher weightage, higher values will get the highest priority. So you can see, of course, the watershed having higher drainage density, the opportunity time for that water to remain in that watershed will be very less. So if the drainage density of that watershed is high priority should be given to the conservation. So the watershed having high drainage density should be treated first, then the watershed having low drainage density. So sub watershed having high drainage density, the weightage is given higher. Now the form factor. Form factor is nothing but ratio of width of watershed by length of watershed, and if the form factor is very high, less priority is given, and if the form factor is very less, the higher priority is given. As you can see, it's a ratio of width by length. If width is less and length is if it is high, very high form factor will get value very less. So if width is more and length is less, so you can see length is less and width is high, like this. So time to particle to travel from this point to channel will be more. And if your form factor is very less, means your width is less and high, means there is a channel available for all the surface particles very near to that erosion point. So all those particles will drain out of this area. So wherever form factor is very high, less weightage is given. Wherever form factor is less, more weightage is given. Similarly, slope, of course, where slope is high, higher weightages are given. Where slope is less, low weightage is given. Now vegetation density, of course we all know, if dense vegetation is there, we don't have to worry, so less weightage will be given. If poor vegetation condition is there or no vegetation is there, higher weightage or higher priority should be given. Now soil barrenness, if you are seeing these are the equations to calculate soil barrenness using list 1 or list 2 data, and this is the equation to calculate soil barrenness using thematic mapper data. These are empirical kind of equations. You can find these equations for whatever sensor you are using, and if soil is exposed, obviously the brightness value whatever you are getting out of this equation will be high, and you have to give higher weightage. So instead of that, we have given a weightage to the texture, because the soil data was available to us. So we have given texture. Otherwise, if you don't have texture information, if your soil brightness index is high, give higher weightage. If your soil brightness index is less, give less weightage. And now you can see the weightage. Now we are going to add all these weightage maps, and the criteria followed here is a narrow band for the higher values and broad band for the, you can see 0 to 30, 30 to 55, 55 to almost 30, here 25, 20, 15, 10. The gap of this is 10, because higher weightage means more is the problem of soil erosion. So we have given narrow width to this class, and final weightage is given 5, or more weightage is given. Now this was the watershed erosion response model. Another approach could be just by analyzing the socio-economic and demographic data of those watersheds. So there are a number of data. You can see the location of those villages in that watershed, whether the village is at the ridge or middle or valley, type of agriculture practice, is it irrigated or unirrigated, how much is the unirrigated land in this village, is it more than 50%, is it between 25 to 50% or less than 25%, what is the land use, this village is under forest or barren or agriculture, how many people are below poverty line. Then other demographical information you can find out and give weightage to these. So now first case study, we have calculated these were the sub-watersheds. This is the drainage density, form factor, this is a slope, this is the vegetation, this is a kharif, this is the rabi crop, so this is the annual weightage to the vegetation, and this is the soil brightness. So these were the values given as per the property of those watershed, and this is a final weightage given to those watershed. As you can see, highest weightage, highest summation was 17, so rank of given to this sub-watershed 1, then the second was 16.5, rank given 2, then the third was 13, rank given 3. Then the 13 here also you have, so third rank will be given to this. Now fourth rank is given to this. So this is how the weightage or the priority will vary if you only consider the technical criteria. Now in second case, we have considered the demographical criteria. So these are the villages in this sub-watershed or this watershed. So we have collected all these criteria. So based on its location, then kind of unirrigated land available, land use, population below poverty line, and other things, we have given the weightage. So the village getting highest total weightage is given priority 1. Now sometimes it may happen that the sub-watershed which you have given priority 1 and this village may not be the same, because here actually erosion is only one criteria, whereas here only the technically like the morphological feature, the soil, the land use is the driving criteria, whereas in this case the demography and socio-economic data is a driving criteria. So the rank may vary for different villages. And the third option could be, we have done this soil erosion annual soil loss thing. Just overlay your sub-watershed boundary on this soil loss and extract the average soil loss for each sub-watershed and give the highest priority to the watershed having the highest soil loss, where you can see here I think 49 point something was the highest soil loss. So the first priority will be given to this sub-watershed. So now we have seen 3 case studies wherein the priority was given to watershed in first case based on its morphology, vegetation and soil type. In second case, the priority was given based on the demographic and socio-economic condition of those watersheds or the villages. And in third case, priority was solely given based on the amount of soil being lost from that watershed. So this is all from my side. Thank you.